Let's try to distinguish your voice. Name.
Yeah.
Now I know you are.
I see.
Yes, I know this is yours. You have two,
Yes.
right?
Yeah.
And Jacob.
Thank you.
Yeah. Good job. I think it's the first time to do the homework. Okay.
We did a different question.
Yeah, but that you did correct. That's all. That's
You
it.
wish to check this one?
Oh, I didn't.
This is all.
Ah, you already finished the homework too. Okay. All right. I'm going to grade you. You did good job. Yours. Oh, okay. I saw the number is question one, so okay. Good. Yeah, I will do that. Okay. Thank you.
Where do you find the time?
Yeah.
Yeah, wait.
When I said to
You
do
didn't
homework.
sleep last night? Oh, the day before.
Yeah.
Uh,
I said just two questions and I.
okay, yeah, just two. So
Yeah.
Man,
So when
he already, I'm like already regretting sleeping last night. I'm like, did I make the wrong call?
you already know everything. So actually, this course we have already studied in Nepal.
ah, similar.
Yeah,
Oh, that's good.
he did very well.
Yeah.
4 out of 5.
Okay.
So he is very big.
So let's start it. I will look at it out of it. You think,
Right information. Actually, all the courses that here we should consider food course, we have already studied in Nepal. Theoretical mechanics, quantum mechanics, first and
Yeah,
second,
yeah.
And
That is, you mean undergraduate or graduate?
graduate.
Okay, you have already graduate
Yeah.
degree in there,
Yeah,
so
yeah.
yeah, that is good, good. So for semi-holonomic, last time I think we reached here, if there is a holonomic such that this non-holonomic constant is just total time duty for this, then we say that is semi-holonomic. Say so it is specification with this. So now we're going to prove all the boundary condition. Condition for this, right? So let's this is all we require, right? And then let's first look if this one is dfr dt and g is a function of qg and qg dot. So when we do the total time duty, I'm going to use a k here. K from 1 to n r shift f r shift qg as k. Okay. Okay. Did you use the same textbook in Nepal?
Textbook?
Textbook,
Goldstein.
the same,
Yeah,
right?
yeah.
Oh, okay.
But
But,
different edition. Edition very different.
that time maybe just first edition, right?
Yeah,
Or
yeah.
almost the same. Okay, and this one, and the second one is partial T, right? And so now we want to see, okay, let's look this one. We introduce the mixture element and see if that happen for semi-holonomic, what this term will be, right? So now let's look at first is partial GR, partial PR, let's use QG dot, okay. QG dot. Is this term? So G alpha is here, then we have a K1 in partial. Okay. Partial, because this function does not depend on the generalized velocity, so we keep here. And this one, when only k to j, so we have this one, right? So then this one does not depend on the, because f does not depend on this general velocity, so that is only when only K produce this summation disappear. And the second one is the partial G, so here let's do this term. Here inside this is again a function of Qj, so we have second order derivative. J. And this one does not belong, so this is still keep it. Then we go to this one, right? So this one is also the second order derivative, partial P, partial J. Now we look this one, right? So now the total term derivative of partial Qg is partial G alpha partial Q J alpha is we're going to do this term for total term derivative, this term. So this term we have summation, right? Because this one is function of if I use K from 1 to n, then the partial second order derivative of partial Q J, partial Q K, and Q K dot. Right, and then we have also the partial second order partial Q, partial Q J. So then let's look this G alpha J. G alpha J is this term, right? This term subtract this term. And you see these two terms are cancelled, right? So we have 0 for all the J from 1 to n, alpha from 1 to n. So all the matrix elements, if not all matrix elements of G alpha J equal to 0, then, okay, because we assume this already satisfied semicolon. So if G has this relation, then we have to find the matrix element capital G alpha J is 0. So next time, when we have this non-polynomial constraint, equation constraint, if it is linear, of course, if not linear, we will not go further. If linear, you just check this one. So this is a condition to double check whether this non-polynomial constraint is semi-polynomial. Okay, that is proof. Okay, and there's other way. Alternately, you can also try to find other ways. So I will skip this part. Now, once we have this, then we'll come back to here. So this is the second case if for the non-polynomial constraint with linear in the general velocity. The Lagrange or general Lagrange equation is this one. Left hand side, same thing. The right hand side have two terms. But now for the semi-hollow, this term disappeared, right? So for now for this one, the Lagrange equation or general Lagrange equation is reduced to G equal to minus, right? Alpha from 1 to m. Here, mu alpha dot partial Qg, partial G alpha partial Qg dot is this one. Here, textbook made mistake, they miss this negative sign. They miss is mu alpha dot, they just say mu alpha. And this must be G alpha, not F alpha, because we want to distinguish F alpha will also is holonomic, and the non-holonomic we usually use G alpha. So that is the correct formula. Okay, and now let's consider in general number 3. So this is for only has a holonomic. We are going to apply this formula here. We introduce this undeterminate Lagrange undetermined multiplier lambda, which is a constant, and f alpha, which is a holonomic, only function of general coordinates and time. But second case, if this constant is not holonomic but with a linear in the general velocity, we have this general Lagrange equation, which in regular set we have two terms. But if this non-holonomic constant is semi-holonomic, then we double check this condition. If that's satisfied that it's semi-holonomic, the general Lagrange equations come to here. Now, let's consider if we have case both holonomic and semi-holonomic together, or not, yeah, that's it. For holonomic and semi. So this case, and we have alpha, we have G alpha, and we have also, since we already said this, this semi-holonomic, I'm going to give this condition here also 0. So that is satisfied. When we have this and this, and also this G alpha, J is 0, then the generalize the Lagrange equation for this system is this textbook does not have this term, so I just give you. Actually, you can derive yourself and just combine. Okay, so here maybe I'm going to use to distinguish different index of alpha from 1 to m, and alpha prime from 1 to m prime, suppose, right? So alpha from 1 to m is lambda alpha, partial f alpha, partial qg, is this term, and plus I can minus because we have negative sign here, negative sign. So the minus alpha prime from 1 to m prime, mu alpha prime dot partial g alpha prime partial q g dot partial g alpha prime. Okay, so this is in case, and we are going to discuss one example about this. Okay. Now number 4. That is for holonomic and non-holonomic is Q. It's linear in Q, right? That is come back to this case. This case is if we have a non-holonomic, but not a semi-holonomic, so we have this term, because this term is non-zero. But now we also include holonomic. So this is a more general case. The Lagrange equation, the right-hand side, we have actually 3 terms, right? So now let's write down here and just summarize. So when we reach to any case, we first analyze the type of the constraint, then we are going to check which one is a formula we are going to use. G minus alpha prime from 1 to 1, mu alpha prime dot partial G alpha prime partial Okay, so that is a summary, and now let's go to some examples. I'm going to do 2 examples. One textbook has already discussed, so I will just skip that one. Example 1. Example 1 is one of textbook, but it is wrong, so I want to go slow and get you to correct that. So, okay, give us the Check G alpha. Okay. So see if it is semi-harmonic. So that is the first job. And then set up those equations of motion. So that is the after two, right? So now G alpha is give us is x dot y squared plus x y dot plus k z equal to 0. So alpha only to 1, right? Only one equation of constraint. And here what we know is there are two information. Lagrangian, so here's the Lagrangian. This is general kinetic energy plus potential energy. Minus V is, this is only single particle. X dot squared plus y dot squared plus V dot squared minus V. V is only function of position. Okay, so that is what we know and ask a question, right? So now, let's do this. First, let's check, right? So the check whether it is a semi-harmonic, we're going to check this one. Okay, so now let's do that. G alpha G is d dt partial G lower G alpha partial Q G dot minus partial G alpha partial Q G, right? So how many? We have Q1 equal to X. We have three general coordinates, right? X, Y, Z. So let's consider G alpha 1. Alpha is 1, right? Fine, you just as an index. So now G equal to 1, so that is d dt partial G alpha partial X dot minus partial G alpha partial X equal to, now let's see. Here, partial X dot we have a y squared, right? D dt y squared, right? This term. No x dot here, this partial x, this term, that is plus y dot. And that equal to 2y dot plus y dot not equal to 0. But text will say 0, so that is wrong. I do not know how they say that's 0. So that is the first time we check, okay. You may stop here because we need all to be equal to 0. One of them is not 0, but let's do others. I think we just do the exercise term. G alpha 2 is d dt partial G alpha partial y dot minus partial G alpha partial y. Now let's see. Partial y dot is this one, right? So that is x. And then partial y here, right? I think this is minus, right? Sorry, that is a minus. Because here it's minus, right? Okay, and this is minus partial G alpha partial y. This term we have is 2y x dot. Again, this is a x dot minus 2y x dot is not equal to 0. Okay, let's check 3. Z. G alpha 3 is d dt partial G alpha partial Z dot minus partial G alpha partial Z, which is d dt. Do we have a G dot? There's no, right? No Z dot. Partial Z is minus k. So that equal to minus k, right, because 0, so that is also not 0. So if it is not semi-hollow, this is sometimes given us this constraint, so we need to double check first. But after check, then we can see which equation we are going to use, right? So now this is the first one we check. Then now we go to next one is we are going to solve the equation motion. Just set up. We will not solve because that is the main part is mathematics, right? So now let's we have a g alpha. Okay, I think that's enough. Now let's go to which equation we are going to select. We have only one constraint. This constraint is non-holonomic, linear in the velocity. So that is this one, right? It's here. We have two terms. So okay, I can use this one. So now that is the first one. I go to second. Let's look because L, right? So now let's first, I mean, okay, just write down the equation. So now we are going to solve the equation of generalized Lagrange. Minus alpha, but here alpha equal to only 1, right? So that is the mu alpha dot partial g out partial q g out minus mu alpha g alpha g. Okay, now I can erase those. So here we have Lagrangian. So now we are going to do is for q1 equal to x, we have partial L partial x is only minus partial v partial x, right? Since it's only potential as a function of x, and the kinetic energy does not depend on the x, right? And then the partial L partial x dot is then x dot, right? Potential does not depend. Okay, so now this side we can have then we have d dt, so that is mx dot minus here, then plus, right? Partial v partial x equal to minus mu alpha dot is only one term. Then partial g alpha partial q g. I think I already did it, right? The first step, right? And this one. That is y squared. Y squared and minus mu alpha g alpha is this one. This step, right? We have a 2y x dot, right? Y dot, okay, 2y dot. So that is 2y minus 1 y dot. Yes. So that is equation 1, if you want to. That is equation 1 for the from this general Lagrange equation. We set up equation motion, and how to solve that. Of course, this one we can simply write here. The right hand side is mx double dot plus partial x. That equal to minus mu alpha dot plus minus mu alpha 2y minus 1 y dot. So this is equation 1. So now we go to second one. Q2 equal to 1. Partial L partial y is again partial minus partial v partial y. Right? Partial L partial y dot. Here is my dot. And then we can have d dt and y dot. Okay, and that is the minus became plus partial v partial y equal to minus v dot. And then the second one is this one. So partial T y partial T alpha partial y dot is x. So we have x and minus mu alpha G alpha 2 is that one is 2x, 1 minus 2y x dot. So then we have m y double dot plus partial v partial y equal to minus mu alpha dot x minus mu alpha 1 minus 2y x dot. That is equation 2. Last one, Q3 equal to z. We also do each individual term. Partial L partial z is minus k, right? Sorry, is partial minus partial. That is potential. Oh, okay, here. We have also okay. The potential partial L partial z dot is mz dot. Then we can have this Lagrange equation is partial L partial z dot partial L partial z equal to here we have I just immediately write down here. I do not need it. Mz dot dot plus partial v partial z equal to minus mu alpha dot, and then partial G alpha partial z squared is 0, right? So that is 0 and minus mu alpha, and then the G alpha 3 is minus k, right? So that is equation 3. Then the remaining part to solve this, you can see here, this equation has x and also has y. This equation has y and x, so they cross. It's not easy to direct, or these equations are not independent of each other. Now, that is the reason why I want to go this is try to play how to prove whether it is semi-holonomic or non-holonomic. The other is a textbook something wrong, so I want to make a correction. Second one, the textbook have this one. There is a rolling loop going down to the inclined surface, so I will not go through that. You can go through yourself and look at the textbook. Now I want to go to another example, which he is not here. He bring this one, right? So now I'm going to work on this, because this one is this case, -3 case.
I think he is preparing for math test.
Okay, yeah.
Yeah.
That is his question, and I'm prepared for him. But that's fine.
Well,
Yeah.
You can,
it.
yeah, he can look this video.
We have test right after this class.
It's very stressful.
Yes, I know that is the first exam, right? You
Yeah.
do not know what
Well,
kind. And
yeah.
it's a closed textbook?
Yeah, close.
I mean, the only reason it's stressful is because, we did qualifiers and just all the time for, studying, taken up by homework and then, I mean, we'll do our best.
Yeah, do your best. Okay.
Okay.
So this example here. I think because this make it bigger since it's the middle of this box, or otherwise you will see the holes. Okay, so now we have R, we have M1 and M2. Now let's give the condition. So that is the condition, for example, poly. Poly, it is direction-based. Now here, this is his question. So now I want to emphasize. When say the the Pauli's birthplace is on the beer, or at beer, not at this surface. It's here. This birthplace at. Okay, and also rotation without sleeping. Otherwise, the roof with this surface. Otherwise, you cannot rotate. That is also his second question. Without rotation. I also give a mass, so I have no space here to mass here. Capital M is the mass of this poly. So that is the first one. Second one about M1. This the surface is also fraction limits between M1 and surface or the table, right? So that is the second condition. M1 and M2. Let's see this. Just write this. Roof. M1 and M2. So the length is the length L and the mass weight. So we do not consider the motion of roof. Mass. Okay, those are conditions. So now, the question is find the motion of M1, M2, and the support. Second, force due to the constraint. We have several constraints. So we are going to analyze. That is advantage of this extending Hamilton's principle. So now it's flat. Okay, we first do the analysis. Analyze the constraint in this case. Okay. The first constraint. Now I'm going to set up these coordinates so that we can select these general points. So I'm going to set the axis here. X, Y. So I'm going to say here, that is from here to here, that is x1. And from here to here, I'm going to say x2. Okay. So once I have this, now the first condition we know this, right? I mean the roof, the L will not change. So that means x1 plus x2 and plus this part, right? That is quarter of the whole conference, right? And minus L equal to FR equal to 0. Or I'm going to FR squared. Right, that is 1. Because this is only a function of the general coordinates, it's the holonomic. So this is a holonomic. Okay. So we have a second one, is this condition. Rolling without slipping, right? So that means any point here, all the rotation, I'm going to use the angle here. R, let's put R here. So anytime I have an angle theta, the rotation be same, the linear velocity on this edge of the police be equal to the velocity of x1 or x2, right? So we have, let's select x2. I'm going to select the G alpha because it's depend on the generalized velocity, so that is non-holonomic, constraint not holonomic, so that is, okay, capital R, that is the linear velocity of this rotation minus x2 dot equal to 0, right? So now I'm going to give okay. Let me erase. I think you remember this, so I can erase this part. Okay. So we first have two constraints, that is combination of holonomic, this non-holonomic, and this, right, this linear in UG. So that is, in general, we are going to apply the equation here. The general force has the part corresponds to this one, the part corresponds, there's a G alpha J. So now we are going to check, okay, no, that's the first one, solution one, right? Then next, we are going to set up this general coordinate. Since for the extending Hamilton's principle, we do not require this one independent, right? So we can select any general coordinates as we want. They are dependent is fine. So we select to characterize motion of M1 on use x1, M2, x2, and then the rotation of pulley is theta. So I'm going to select 3. Definitely they are dependent, right? So you can, if you double check the number of independent or degree of freedom, you will see that this 2 is not 3. Okay. So once we select this, so we are going to check whether it is semi-holonomic. If yes, then we can go to next, which equation, generalized equation, Lagrange equation we are going to use, right? So, okay, first one for Q1 equal to x1, we are going to G alpha 1 is d dt partial G alpha partial x1 dot partial G alpha partial x1, right? So G alpha is here. There's no x1 dot, no x, right? No x1, no x1 dot, right? So that's 0. At least this is one works, right? So now we are going to check other 2. Then for Q2 equal to x2, G alpha 2, let's see whether it is satisfy the semi-holonomic condition, x2 dot minus G alpha partial x2 is here. So we have a minus 1, d dt minus 1, and minus 0, right? Because no term, so that is 0, right? Constant time divided is 0. So, okay, the last one, let's do that. d dt partial G alpha partial theta dot minus partial G alpha partial theta. So partial theta dot is here, is R, right? Minus partial G, there's nothing, that's a 0. Because R is constant, so that's 0. Okay, yes. So this is a semi-holonomic constraint. If that is the case, now we go to next. We are going to we are going to solve, right? So first the transformation equation, which we are going to find the relation between this x1, x2, and theta transformation equations. So here, x1, from here, x1 equal to L minus pi r L2 minus x2, right? And x2 is fine, so I will not, since so now, and then this r theta dot is equal to x2 dot. Then immediately if we do the derivative, so we have x1 dot equal to minus x2 dot, and also if we do double conjugative is minus x2 dot. So I'm going to say this equation 1. Then this one, we can also have a theta, r double theta dot is x. So here we have the relation between those general coordinates, and you can see they indeed depend on each other. Now, next step is we are going to write down this right? So kinetic energy is the first particle, the second particle, and the third one is rotation, right? Half m r squared is rotation inertia, and theta dot, right? Okay, now if I select v equal to 0 is this line along the x. So the m1, because it's a move horizontally, that's a constant, right? Whatever it moves, but it's this potential is only gravitational potential, right? So I'm going to say that is just some constant. Or, yeah, that's a constant. And plus 0, because the rotation of the pony set up with the origin center of the pony, so that is the second mass is just a 0, then that's 0. And minus m2 g x2, right? Because I said x2 is here, x-axis. So that is potential. Then we can write down the Lagrangian is half of m1 x1 dot square plus half of m2 x2 dot square plus, keep half here, theta dot square and minus plus, right? Minus maybe plus m2 g x2. That is Lagrangian. Okay, which Lagrange equation we are going to use? Okay, that's since here we already proved this semi-holonomic. So now, before we go to that, we can, once we have a Lagrange, we can do all this the partial rule. So now let's look at for Q1 equal to x1. How many? We have partial L, partial x1. Partial L, partial x1 is 0, right? No x1 here. And then the partial L, have space, I use a whole new ones. So here, partial L, partial x1 equal to 0, partial L, partial x1 dot is here. n1 x dot, x1 dot. And then, since we have a holonomic, we have also a semi-holonomic, so the right-hand side of Lagrange equation, we have two terms, right? So now we need that term, so like partial f alpha, partial x1, we need this, but this is 1, right? Because here, partial f, partial x1. And then the last one, partial g alpha, partial x dot, x1 dot. 0, right? No x1 here. So that is for the first general coordinate. Then now for the second one, Q2 equal to x2. Again, we look at this each term. Then we are going to substitute those into this Lagrange equation. Partial x2 equal to this one, right? Minus m f did sorry, plus. Here, this one. m2g. Partial L, partial x2 dot is m2 x2 dot. Partial f alpha, partial x2 is 1. Here, we have x2 here. Then the last one, partial g alpha, partial x2 dot is minus 1, right? It's this one. All right, so now next one is for the Q3 equal to theta, partial L, partial theta. Do we have? We do not, right? Zero, partial L, partial theta dot. Yes, we have this. So this two factor two can disappear. And square theta dot. Then the partial F alpha partial theta, 0, right? No angle. Then the last one, partial G alpha partial theta dot is R. This one. Okay, once we have those, so now we go to 7. Let's apply this Lagrange equation, generalized Lagrange equation. This holonomic, combined holonomic and semi-holonomic, that's equal to, since let me just use this, since alpha only 1, right? I don't need summation. Partial F alpha, partial QG minus mu alpha dot, partial G alpha, partial Q dot. We need to apply this equation, right? So now again, for each one, so now let's consider for Q1 equal to S1. We already this here, right? So now the first term, dt, this term is m1 x1 dot. So now we have m1 x1 double dot, right? And this one's 0. So right hand side only this term. Now right hand side, partial fr partial x1 is 1. So we have a lambda. And the partial g alpha partial x1 dot is 0. So now this is equation 3. That is for x1. Now let's go to for x2. And for q2 equal to x2. Again, just immediate. Yes, we already have. So I just do the immediately. So now dt, d partial L partial x1 2 dot is here. So that is m2 x2 dot double dot. m2 x2 double dot. And we have non-zero term. It's partial L partial x2 is m2g. So that's minus m2g. So that is left hand side. Let's go to the right hand side. Okay, yes. Right hand side. This one is 1, right? Partial fr partial x2 is 1. And this is minus 1, so we have lambda alpha. It should be minus right here. Minus mu alpha dot, but we have a minus plus. Mu alpha dot. So this equation number 4. And the last one, Q3 equal to theta. Again, now let's see. This is a constant, right? So the double theta double dot. So that is half of m r squared theta double dot. Yeah. And this term is 0. So right hand side is only this term. Now let's go to right hand side. Partial f partial lambda is 0. Partial theta is 0. Only this is r. So there's no lambda, and this is only mu alpha dot r. Equation 5. So the remaining part we are going to apply the equation 1, 2, 3. So you see 1 gave us information between the x1 double dot and x2 double dot, and equation 2 also gave x2 double dot and theta double dot. Then the equation 3 gave us the lambda. So if we substitute equation 3 here, then that is only function x1 double dot. Then we use equation 1, so x1 double dot become negative x2 double dot, right? Then this one I'm going to put here. So that means substitute equations 1, 2, 3, 5, 2, equation 4. So now the left hand side equation, now I'm going to m2 x2 double dot minus m2g, not p, right? Now this lambda is, let me write that in there. Double dot, right? Equation 3. And then this one, so this is a minus because this is a plus, this is minus. You see the R cancelled. Then we have 2mr theta double dot, right? I'll check that. Yes, to n. Then I go to next. Since equation 1 not equal to negative, right? And this one is positive. So theta double dot is R theta dot is half of, sorry, this is minus. Because this is plus. So you see, this is only equation for x2 double dot. Then you can immediately get the x2 double dot, you just combine together, you will see that this denominator is this 3 mass sum together, and the numerator is m2g. And then, okay, the others are easy, so you just use. So now we are result x1 is double dot is negative x2 double dot, so that you just make sign. Theta double dot is, you just use that equation is r x2 double dot, right? Just very easy. So we get the equation of motion. Now I think we finished this one. So now we go to the next one. The next one. So now solution right? Okay. So now if we just follow 1, 2, 3, 4 to now 7. Now we are going to find the general this one, right? That is a generalized force that associates the force of constant. That is defined as then we have 3. So now let's do that. Again, we also do 1 by 1. Q1 equal to x1. So I'm going to say the capital Q1. That is lambda. Okay. Here, what is lambda? If you come equation 3, lambda is m1 x1 double dot, right? So very easily, let me just first write down here, and then I can. This is the lambda. Since this is a 1, right? Partial FR partial is 1, and then second one 0. So only lambda. This term 0, right? So that equal to lambda is m1 x1 double dot. You just take x1 here. Or if you substitute x2 double dot is negative. Okay, so that force, think about this force. And yes, it is in unit is Newton, right? Because you see the mass acceleration. So that unit is which force? This force will around x1, right? Because it's isoelectric code, so that is here. That is tension, right? So that is tension. X1. Okay, let's do the second. For Q2 equal to x2, then the capital Q2 is lambda partial, that is also 1, right? Okay, this one that is minus 1. So is 1 minus mu alpha dot. Because this is a plus. It is nothing but this one. Right? This is, so you just look here. Right? And then lambda we have is m1 x1 double dot. And then mu alpha is this formula, right? So that is negative half of mr theta double dot. Then we know x1 double dot is minus x2 double dot, and this one is r x2 double dot, right? So r cancel. Then you will have minus m1 plus 2 and x2 double dot. And x2 double dot is already here. So that is second one. And the last one. Last one, this one 0, so only this term, so that is nothing but this one, minus mu alpha dot r, and then mu, this one is nothing but half of m r theta double dot over half of m r x2 double dot. Okay, here, suppose this one is around x2, right? So that is this one, q1. But the negative, so that is r, right? So that is, this is also tension along x2. How about this one? This was theta. Theta is rotation, right? Rotation is possible, that is this top, right? Q3, so that is a top. If I say along the Q theta, you know this tangent theta. Theta direction is perpendicular to. So that, yes, everything we answer, right? That is the advantage of this extending of Hamilton's principle. So now, this advantage we show here. Now we want to also show the more advantage is, so far we deal with is dynamic system, right, or mechanic system, how the dynamics motion of particle system. But this equation, which the Lagrange equation, which can extend it to even not dynamic system like electron magnet system. So one of the advantage is we can extend the general Lagrange equation to other system, other field. The example let's discuss electron magnetic system. Okay. I will stop in time, so you will have time. So let's just cover this, I think, for examples. So example, right? So now example like this electric circuit. So for the electric, how to apply the Lagrange equation, we need this sum of the analogs between these two, then we can very easily to apply this analogs. Okay, so that is the mechanics. That is the electron. Actually, this is electric in this case, but that's just in general. So, in the mechanics, we are going to this mass, right? Mass inertia, or inner, the inertia, so system mass in this circuit correspond to this one is L. L is inductor or inductance. So that with this correspond to, and then the next one is a general coordinate. This one correspond to here is charge. Because in the circuit we're looking more is motion of charge, right? So that is it corresponds to each other. Then here the capacity, we have the capacitor, right? We have stored energy, capacity, or capacitance. Okay, capacity is 1/C. That corresponds to this, like a Hall's law, the string, constant, right? String constant. In the Hooke law, right? So like this vibration, and we know that this capacitor also charge, this charge is like this. Then the resistor, so that is here, resistor or resistance is as correspond to the K. I use the dissipation. Remember we discussed the dissipation constant. That is for this and the last one is the current. Current I corresponds to the generalized velocity. Current equal to the charge dot, right? And the generalized velocity or just velocity, right? Okay, with this corresponds, so then when we have the circuit, we just try to find how many elements in this, and we can write down this kinetic energy, potential energy, then we can apply the Lagrange equation to each case. So keep in mind this, now let's do examples. Three, right? We have a two. That's another case. Oh, I have another one. I haven't finished. Okay. Before that, let's see. Still this one. So there's a kinetic energy here, right? In this dynamics is in this one, but in this circuit is just since the mass is this L, right? Inductance. So that is only associated with this one. Q dot is current, right? That is this one. So that is kinetic energy, and then potential energy. Potential energy here, if we have a potential energy like this spring, so that corresponds to here is capacitor energy stored in the capacitor. Then for the resistor here, we have a dissipation function. Remember that is a function of velocity, and this is for this term is a resistor. Is dissipation function in this case is half of R resistor and Q dot square. The last one is this external potential. I'm going to use external. It's minus Q. Let me use this one. So that is another potential. If in this mechanics external potential. Okay. So now let's do. Examples. I want to go is little because we also need to finish chapter 2 before the break, so we can go to our later exam. Okay, now go to examples. 3. So that is R. Sorry, not R. Let's go to first without the resistance. Only this capacitor and the inductor is LC circuit. LC circuit, we have capacitor, we have L, and no any others. So this L is C. And in this case, now we just set up Lagrange immediately, right? T minus U here. So T. Do we have a kinetic energy? Yes, it's right. So we have write down. since we have this inductor half of Q dot square. And then this potential is this one. Right, so the minus half of CQ square. Okay. Then you can see here, there's no any other force, right? So that the Lagrange speed Q, in this case, only the general coordinate is only Q, right? So Q dot minus Q equal to 0. And now let's do that. So here we have do this one, that is L Q dot to Q double dot, and this minus is this one is minus C, right? Q equal to 0. So this equation is very simple. You know that is the oscillation, right? So that gives solution Q is Q naught as initial condition, cosine omega naught T, and omega naught is this ratio of, you know, this this time constant, right? Remember this. Okay, so that you see very easy if we just try to make this connection or analogs between these variables, then we can easily obtain this. Now the second one, let's consider if we have a resistance. RC circuit, since this one is, we have a resistor. Here we also have an external EMF, so that is RC. So, you have a question? That's okay. Which part? This equation, right?
Yeah, negative sign. I think
Sign, confused with sign.
Wait a moment. This is minus, correct, right? And then,
this equation of motion.
this minus plus, yes, you're right. Okay, yeah, minus, here we have minus, yes. So now, let's see here, again, we just immediately write down this Lagrangian T minus U. But, yeah, let's write down this one first. So now let's T 0. No this inductor, right? So only the potential minus half of CQ squared. But we have another potential, external potential. Yeah, this one. So that is minus became plus Q, actually. Okay, so that is, and then we are going to apply this equation here, equal to what? We have a resistance. So we have a dissipation term, this one. So that equation is equal to minus partial F partial Q dot. Yes. Or you just move to the right hand side. So this equation gave us partial L partial Q dot 0, right? No this term. Minus, so this one became plus. CQ, here it became plus, but this one's minus actually, right? Equal to minus. So now this one is F tilde. Then we start we have a R. Here we go. Then you are going to solve this equation. So the solution, just do not spend time to that. You will see the solution is, I give you a solution, epsilon, capacitor, or capacitance, and then T minus P or RC. Oh, this is the time constant. So this is the oscillator. So this is charging, right? When we charge the circuit, or charge this capacitor. So that is the formula. If without this one, and you can do that. So let me stop here. I'll give you more time so you can stop here. The others, textbook has examples, I don't want to spend time. The next Tuesday we start for discuss conservation, which is the last topic of this chapter 2. Okay, good luck.
Thank you.
Yeah. Can you see him? Can you pass his homework to him?
Yes,
He will
yes.
attend this.
Okay.
Okay, yes, thank you. Maybe he needs this weekend for